Hayabusa2 Japanese, Hayabusa2, Peregrine Falcon 2, is an asteroid sample return mission operated by the Japanese Space Agency, JAXA. It follows on from Hayabusa and addresses weak points identified in that mission. Hayabusa2 was launched on 3 December 2014 and rendezvoused with near-Earth asteroid 162173 Ryugu on 27 June 2018. It is in the process of surveying the asteroid for a year and a half, departing in December 2019, and returning to Earth in December 2020. Hayabusa2 carries multiple science payloads for remote sensing, sampling, and 4 small rovers that will investigate the asteroid surface to inform the environmental and geological context of the samples collected. Mission overview. Asteroid 162173 Ryugu, formerly designated 1999 JU-3, is a primitive carbonaceous near-Earth asteroid. Carbonaceous asteroids are expected to preserve the most pristine materials in the Solar System, a mixture of minerals, ice, and organic compounds that interact with each other. Studying it is expected to provide additional knowledge on the origin and evolution of the inner planets and, in particular, the origin of water and organic compounds on Earth, all relevant to the origin of life on Earth. Initially, launch was planned for 30 November 2014, but was delayed to 3 December 2014 4:22 Coordinated Universal Time, 4 December 2014 13 hours 22 minutes and 4 seconds local time on AHIIA launch vehicle. Hayabusa2 arrived at Ryugu on 27 June 2018, and it is expected to survey the asteroid for a year and a half, during which time it will collect samples 3 times. The mission plan calls for it to depart in December 2019, and return the samples to Earth in December 2020. Compared to the previous Hayabusa mission, the spacecraft features improved ion engines, guidance and navigation technology, antennas, and attitude control systems. A kinetic penetrator will be shot into the asteroid to expose pristine sample material. Funding and history. Following the partial success of Hayabusa, JAXA began studying a potential successor mission in 2007. In July 2009, Makoto Yoshikawa of JAXA presented a proposal titled, "Hayabusa Follow on Asteroid Sample Return Missions." In August 2010, JAXA obtained approval from the Japanese government to begin development of Hayabusa2. The cost of the project estimated in 2010 was 16.4 billion yen, $146 million. The primary contractor NEC built the 590 kg (1,300 pounds) spacecraft, its Ka-band communications system and a mid-infrared camera. Hayabusa2 was launched on 3 December 2014, arrived at asteroid Ryugu on 27 June 2018, and remained at a distance of about 20 km to study and map the asteroid. In the week of 16 July 2018, operations were begun to lower this hovering altitude. On 21 September 2018, Hayabusa2 ejected the first 2 rovers, Rover 1A and Rover 1B, from about 55 meters altitude that fell independently to the surface of the asteroid. Spacecraft. The design of Hayabusa2 is based on the first Hayabusa spacecraft, with some matured improvements. It has a mass of 610 kg (1,340 pounds) with fuel, and electric power is generated by bilateral solar arrays with an efficiency of 2.6 kW at 1 astronomical unit, and 1.4 kW at 1.4 astronomical units. The power is stored in 11 inline-mounted 13.2 Ah lithium-ion batteries. Propulsion. The spacecraft features 4 solar electric ion thrusters for propulsion called Mu-10, one of which is a backup. These engines use microwaves to convert xenon into plasma ions, which is accelerated by applying a voltage from the solar panels and ejected out the back of the engine. The simultaneous operation of 3 engines generates thrusts of up to 28 millinewtons. Although this thrust is very small, the engines are also extremely efficient. The 66 kg of xenon reaction mass can change the speed of the spacecraft by up to 2 km per second, 4,500 miles per hour. The spacecraft has 4 redundant reaction wheels and a chemical reaction control system featuring 12 thrusters for attitude control, orientation, and orbital control at the asteroid. The chemical thrusters use hydrazine and MON-3, with a total mass of 48 kg of chemical propellant. Communication: the spacecraft has 2 high-gain directional antennas for X-band and Ka band. Bit rates are 8 bits per second to 32 kilobits per second. The ground stations are the Yasuda Deep Space Center, Uchinora Space Center, NASA Deep Space Network and ESA's Malurgu Station. Navigation: the Optical Navigation Camera Telescope is a telescopic framing camera with 7 colors to optically navigate the spacecraft. It works in synergy with the Optical Navigation Camera Wide Field and with 2 star trackers. In order to descend to the asteroid surface for sampling, the spacecraft will first release up to 5 target markers in the selected landing zones as artificial landmarks with highly reflective outer material that is recognized by a strobe light mounted on the spacecraft. The spacecraft will also use its laser altimeter and ranging and other sensors during sampling. Instruments. The Hayabusa2 payload incorporates multiple scientific instruments: remote sensing, optical navigation camera (ONCT), ONCW1, ONCW2, near-infrared camera (NIR3), thermal infrared camera (TIR), light detection and ranging (LIDAR). Sampling device (SMP), small carry-on impactor (SI), deployable camera (DCAM3). 4 rovers: Mobile Asteroid Surface Scout (Mascot), Rover 1A, Rover 1B, Rover 2. Topic: Remote sensing. The optical navigation cameras (ONCs) are used for spacecraft navigation during the asteroid approach and proximity operations. They will also remotely image the surface and search for interplanetary dust around the asteroid. ONCT is a telephoto camera with a 6.35 degree x 6.35 degrees field of view and several optical filters carried in a carousel. ONCW1 and ONCW2 are wide-angle 65.24 degree x 65.24 degrees panchromatic 485 to 655 nanometers cameras of nadir and oblique views, respectively. The Near-Infrared Spectrometer (NIRS-3) is a spectrograph operating at wavelengths 1.8 to 3.2 micrometers, intended for analysis of surface mineral composition. The Thermal Infrared Imager (TIR) is a thermal infrared camera working at 8 to 12 micrometers, using a 2-dimensional microbolometer array. Its spatial resolution is 20 meters at 20 kilometers distance or 5 centimeters at 50 meters distance. It will be able to determine surface temperatures in the range -40 to 150 degrees Celsius. The light detection and ranging (LIDAR) instrument will measure the distance from spacecraft to the asteroid surface by measuring the time of flight of laser light reflection. It operates over the altitude range 30 meters to 25 kilometers. When the spacecraft is closer to the surface than 30 meters during the sampling operation, laser range finders (LRFS-1, LRFS-3) are used to measure the distance and the attitude of spacecraft relative to the terrain. Another device, LRFS-2, monitors the sampling horn to trigger the sampling projectile. LIDAR and ONC data will be combined to determine the detailed topography, dimensions and shape of the asteroid. Monitoring of a radio signal from Earth will allow measurement of the asteroid's gravitational field. Rovers. 'Hayabusa2 carries 4 small rovers to investigate the asteroid surface in situ, and provide context information for the return samples. All 4 rovers will move around by short hops, and none is equipped with wheels due to the minimal gravity of the asteroid. They will be deployed at different dates from about 60 meters altitude and fall freely to the surface under the asteroid's weak gravity. The first 2 rovers landed on asteroid Ryugu on 21 September 2018. Minerva 2. Minerva II is a successor to the Minerva lander carried by Hayabusa. It consists of several separate subsystems. Minerva E1 is a container that deployed two rovers, Rover 1A and Rover 1B, on 21 September 2018. It was developed by JAXA and the University of Aizu. The rovers are identical with a cylindrical shape, 18 cm diameter and 7 cm tall, and a mass of 1.1 kg (2.4 pounds) each. They move by hopping in the low gravitational field, using a torque generated by rotating masses within the rovers. Their scientific payload is a stereo camera, wide-angle camera, and thermometers. Solar cells and double-layer capacitors provide the electrical power. The Minerva E2 container holds the Rover 2, developed by a consortium of universities led by Tohoku University in Japan. This is an octagonal prism shape, 15 cm diameter and 16 cm tall, 5.9 × 6.3 in, with a mass of about 1 kg (2.2 pounds). It has two cameras, a thermometer and an accelerometer. It has optical and ultraviolet LEDs for illumination to detect floating dust particles. Rover 2 carries 4 mechanisms to hop and relocate. Mascot. The Mobile Asteroid Surface Scout Mascot was developed by the German Aerospace Center in cooperation with the French space agency CNES. It measures 29.5 cm x 27.5 cm x 19.5 cm and has a mass of 9.6 kg (21 pounds). Mascot carries 4 instruments: an infrared spectrometer (micromega), a magnetometer (MASMAG), a radiometer (MARA), and a camera (MASCAM) that image the small-scale structure, distribution and texture of the regolith. The rover is capable of tumbling once to reposition itself for further measurements. It collected data on the surface structure and mineralogical composition, the thermal behavior and the magnetic properties of the asteroid. It has a non-rechargeable battery that allowed for operations for approximately 16 hours. The infrared radiometer on the InSight Mars lander, launched in 2018, is based on the Mascot radiometer. Sampling. The spacecraft will collect 3 samples and store them in separate sealed containers inside the sample return capsule. The 3 desired samples are surface regolith that exhibits traits of hydrous minerals, regolith with either unobservable or weak evidence of aqueous alterations, and excavated sub-surface material. The minimum desired amount per sampling is 0.1 grams, but the system has capacity to collect up to 10 grams per sample. The first sampling is scheduled for late October 2018, the second for February 2019, and the third will be during April to May 2019 on excavated material dislodged by a kinetic impactor shot from a distance. Surface samples. Hayabusa2's sampling device is based on Hayabusa's. In late October 2018, the spacecraft will approach the surface of the asteroid with a sampling horn. When the horn touches the surface, a projectile 5-gram tantalum bullet will be fired at 300 meters per second into the surface. The resulting ejecta particles are collected by a catcher at the top of the horn, which the ejecta will reach under their own momentum under microgravity conditions. Subsurface sample. The third and last sample collection will take place during April to May 2019 of material deeper into the subsurface, which has not been subjected to space weathering. This requires removing a large volume of surface material with a substantial impactor. For this purpose, Hayabusa2 will deploy the Small Carry-On Impactor, a kinetic impactor consisting of a 2.5 kg (5 pounds) copper projectile shot to the surface by an explosive propellant charge. Following Psi deployment, Hayabusa2 will leave behind a deployable camera DCAM-3 to observe and map the precise location of the Psi impact, while maneuvering to the far side of the asteroid in order to avoid debris from the impact. Approximately 40 minutes after separation, when the spacecraft is at a safe distance, the penetrator will be fired into the asteroid surface by the detonation of 4.5 kg (9.9 pounds) shaped charge of plasticized HMX for acceleration. The copper impactor will be shot to the surface from an altitude of about 500 meters, and it is expected to excavate a crater of about 2 meters in diameter and expose pristine material. Hayabusa2 will wait about 2 weeks for the floating debris to clear from the site before descending into the newly formed crater to retrieve a sample. Sample return. The spacecraft will collect 3 samples and store them in separate sealed containers inside the Sample Return Capsule (SRC), which has a thermal insulation, 40 cm external diameter, 20 cm in height, and a mass of approximately 16 kg. At the end of the science phase in December 2019, Hayabusa2 will use its ion engines for changing orbit and return to Earth. When Hayabusa2 flies past Earth in December 2020, it will release the capsule spinning at 1 revolution per 3 seconds. The capsule will re-enter the Earth's atmosphere at 12 km per second, and it will deploy a radar reflective parachute at an altitude of about 10 km, and eject its heat shield, while transmitting a position beacon signal. The sample capsule will land in the Woomera Test Range in Australia. The total flight distance would be 5,240,000,000 km. Once on Earth, any volatile substance will be collected before the sealed containers are opened. The samples will be curated and analyzed at JAXA's Extraterrestrial Sample Curation Center, where international scientists can request a small portion of the samples. Status. On 21 September 2018, the Hayabusa2 spacecraft ejected the first 2 rovers, Rover 1A and Rover 1B, from about 55 meters altitude that fell independently to the surface of the asteroid. They are functioning nominally and transmitting data. The Mascot rover deployed successfully on 3 October 2018 and operated for about 16 hours as planned. The first of 3 sample collections is planned for late October 2018, the second for February 2019, and the third will be during April to May 2019 on excavated material dislodged by the impactor. Potential mission extension. When the spacecraft returns to Earth and delivers the sample capsule in December 2020, it is expected to retain 30 kg of xenon propellant, which can be used to extend its service and fly by new targets to explore. One prime candidate is asteroid 2001 WR1 for a flyby on 27 June 2023. See also: OSIRIS-REx, Procyon, Hayabusa Mk2 Japanese minor body probes, Susei, Hiten, Hayabusa, MMX, Okeanos, a proposed mission to Trojan asteroids. Notes. References. External links. Hayabusa2 project website, JAXA Hayabusa2 website, Asteroid Explorer Hayabusa2, NEC, Hayabusa2 images scientific commentary, University of Tokyo, Hayabusa2 3D model, Asahi Shinbun.